Okay, I should be recording. Screen is shared. Good. Thank you all for coming. Obviously, since this is being recorded, uh, this will be up on Blackboard. But what I want to do is make the key with you all here, and you can ask questions along the way. And I have the final more or less made. So for people who are here / for people who end up watching, let's just say I'll make it worth your time. Okay. So I'd say that this page is very much worth your time for the final. Some might say, might, show up in some ways on the final. Perhaps, maybe. I will say that these sorts of problems, I don't know a better way unless you sort of know the mechanism of solving these than to just sort of be able to notice like what functional groups you have and then what reactions those do. So ketone, borohydride, BH4 minus. What is this reactive? We use this in lab. What does this add? Turns a ketone into an alcohol. That's right. So what does a ketone have here, a carbonyl? To become an alcohol, what needs to happen? That carbonyl needs to break. And what do you need to gain then? A hydrogen. So BH4 minus is a source, essentially, of, oh gosh, hydrogen with a lone pair, or H minus. H minus. And so if you wanted to template these answers almost, if you know a ketone is going to an alcohol, then you get rid of the carbonyl, put your O. This H and HCl ends up on the oxygen. And then whatever here is in the first step is what else gets added to the carbonyl carbon. So if it's a hydride, it's going to be a hydrogen. So we can draw, you could draw it like this, or if you want to explicitly show the hydrogen that was added, you can also do that. But either of those would have been acceptable. So ketone and hydride goes to alcohol. Okay, this is an alcohol. Where does the H come from on the alcohol? HCl, okay, so we don't really care about that. What sort of reagent is this? A carbon-magnesium bond. Grignard, which is an organometallic. Yep, Grignard. That's organometallic. What are these a source of? What do they act like? If hydrides are H minus, what does a Grignard react as, or all organometallics act as? Yeah, like a CH3 minus. So in this case, H3C MgBr, that is equivalent to H3C minus and MgBr plus. So it's actually a covalent bond, but sometimes it's easier to think of these hydride and organometallic reagents as like ionic compounds, because then it's very easy to see what they react as. Well, CH3 minus has excess electrons, so yes, Susie?
I'm just wondering, so like with the Grignard reagent, it's usually drawn with like an ether or the diethyl ether in their notes. Is that just like implied as a solvent?
Yes. Yes, it's implied as a salt.
And then is it the same thing with ethanol for the first hydride?
Yes, yes.
But like if we have fill in blank for putting in.
You would just have to supply the NaBH4 or the Grignard. So if you want to give the solvents, go ahead, but we haven't really focused on solvents that much in the class, so just the reagent. So what on this compound, what is over here? Well, there's a methyl group, right? Where do we think that methyl group is coming from? The Grignard. So if you're going backwards, the Grignard's adding that, get rid of your H, get rid of your methyl. You're going to be left with, well, a carbonyl that has a hydrogen and a 1, 2, 3 propyl group. 1, 2 on it. So this is an aldehyde with the Grignard reagent going to an alcohol. Erase that for the key. Okay. Well, what is this reagent here? Step 1. Also a Grignard. So it's the same sort of reaction here. We're going to add this group to the carbonyl. What else gets added in the second step? Hydrogen. So we start with H3C and H. We're going to add 3 carbons, 1, 2, 3. And then what happens to the carbonyl? Becomes an alcohol. OH. So this is again an aldehyde, Grignard, an alcohol. Notice that these are all the same products. I'm just showing here that you can make them through a lot of different ways. You can start with that ketone with a hydride. So this ketone had the 2 carbon groups already there, and it needed the hydrogen. This aldehyde had the hydrogen and the propyl group, and it needed the methyl group, so you get methyl Grignard. This aldehyde had the hydrogen and the methyl group, and it needed the propyl group. So there's a lot of different ways that you can make this compound with hydrides, Grignard reagents, and then carbonyl derivatives. Okay, so what sort of functional group is this? O, C double bond O, O. It's an ester, so it's almost like a carboxylic acid. So a carboxylic acid is O, C double bond, or C double bond O, OH. So the only difference between an ester is ester has a carbon here, whereas a carboxylic acid has a what? An H, or a proton. Acid. Okay, ester, what sort of reagent is this? Lithium, aluminum, what's the last word? Hydride, yep. Hydride. Hydrides are a source of what? Hydrogen, but specifically, so a proton, actually, this is a proton is H plus. So, right, so here's a hydrogen atom, H dot, H with an electron. A proton is a hydrogen atom minus an electron. A hydride is a hydrogen atom plus an electron. So why does this act as a hydride? Well, if we look at an aluminum hydrogen bond, this bond, what is it polarized towards? Where's the partial minus charge? Towards the hydrogen. Aluminum, isn't there supposed to be like a big periodic table in this classroom?
It's on the backboard of the phone. It's like behind the two boards here, like if you have boards down.
Oh. Oh. Aluminum here, hydrogen here. So electronegativity increases, so aluminum is to the right of hydrogen, but going down, electronegativity decreases. It turns out it decreases more going down than it increases going to the right. In your note packet, you can also see I gave the values that aluminum is less electronegative than hydrogen. So an aluminum hydrogen bond, the H has a partial minus. That's why hydrides act as a source essentially of H minus. So if a ketone gets one equivalent of a hydride, how many equivalents of a hydride does an ester get? 2. So that's a really important thing to know for the test, that carboxylic acid derivatives can get 2 equivalents of a hydride or of what? Organometallics, so like organolithium compounds or Grignard reagents. Okay, so the ester getting 2 equivalents of the hydride is going to take it down to a what? So if it gets 1 equivalent of the hydride, let's see what we would get. Do the mechanism. The margins here. HAlH3 minus. I want to make a bond between hydrogen and the carbonyl, so I take the electron pair of the bond to the carbonyl, break the carbonyl bond. O minus H O that. This is a tetrahedral intermediate. That's an important thing for the exam. To know that tetrahedral intermediates have sort of O minus structure right there. What happens though when you have a tetrahedral intermediate with a carboxylic acid derivative? What do we have bonded to that carbon? Which can act as a leaving group. So reform your carbonyl to kick out your leaving group. That forms a aldehyde plus O minus. So we've gone from basically one O minus species to another O minus species. So probably that's reversible because I guess the one thing that's favoring this side of equilibrium is a C double bond O versus a C single bond O. So energetically, we gain, basically go down in energy because we form a double bond. But these are about as basic as each other. But we also have another equivalent of hydride. So there's 4. So this can act as 4 H minuses. This is an aldehyde. What happens with an aldehyde and a hydride? It gets what? It goes to an alcohol. So what happens overall is you form this alcohol. These 2 hydrogens are the hydride hydrogens. Where did this hydrogen come from? HCl. Okay, so ester, and here's a good question that you maybe should know. Can sodium borohydride reduce an ester? These borohydride and aluminum hydride are both sources of hydride, H minus. Boron is here, aluminum is here. So if you have a BH bond, B is going to be closer in electronegativity to hydrogen, right? So if you have a tug of war game, hydrogen and boron close in electronegativity, does that end up with more partial minus on hydrogen or less partial minus on hydrogen relative to an aluminum hydrogen bond? Less. So in this case, think of hydrogen as like a big muscly person. Boron is slightly less muscly person. Aluminum, though, is let's say a very not muscly person. So we're going down in muscle mass, going from boron to aluminum. We're losing electronegativity. Hydrogen is able to pull more electron density from the less muscle massy person, aluminum, the less electronegative than it is from boron. So the hydride, aluminum hydride, is a stronger hydride. So AlH4 is a stronger H minus hydride than borohydride, BH4 minus. So more nucleophilic, because hydrides, they have an excess of electrons, so they're going to act as an electron donor, which is a nucleophile. Esters OR versus ketones. Which one is more electrophilic? Which carbonyl? It's actually the ketone is more electrophilic. The lone pair on oxygen here, remember, can do resonance, which would stabilize the carbonyl pretty terrible. The case of the ketone, the carbonyl is stabilized by the inductive effect and hyperconjugation. Learned that in lecture, I don't know, 31 or 2. Here, full-on resonance can stabilize the carbonyl. So you might think, well, can't oxygen also inductively, like, isn't there a dipole towards oxygen that makes that more partial positive? That is true. It's just a competing effect. The resonance effect makes the carbonyl less electrophilic. The inductive effect makes it more electrophilic. Just one of the things that we need to know is that resonance is one of our stronger electronic effects. So the resonance effect matters more and actually sort of favors the carbonyl being therefore less electrophilic than the ketone. So in our note packet, I have this scale here. The aldehydes and ketones, they end up between acids and esters on one side, so they're more reactive, more electrophilic than these. They are less electrophilic than those. Okay, back to our review.
So would that mean that sodium borohydride would not react with an ester?
Sodium borohydride would not react with an ester. Yes.
Okay.
So it's a good question. So if you have something that is very electrophilic, do you need something very nucleophilic to react with it? No. If you have something that isn't very electrophilic, then you need something that is more nucleophilic to react with it. Like if you have a friend who, let's say they're a party animal, do you need a lot of encouragement to make them go out to the scope? No. So if someone is a very good electrophile, a party animal, they don't need a lot of encouragement from you as a nucleophile to go to the scope. Let's say you have a friend, though, that is sort of an introvert. So they're a weak electrophile. What do they need more of?
Encouragement.
They need more encouragement. They need more nucleophilicity. They need a stronger nucleophile to go out to the scope, to react. Does that answer it? Okay. So now that we have an alcohol and a carboxylic acid and a strong acid, so this is an important one to know. This is called a Fischer esterification. So when you have an alcohol and a carboxylic acid with H2SO4 or just a strong acid, essentially what happens that bit, this bit, that bit, you swap them. So all of the nucleophilic acyl transfer reactions are swapping whatever leaving group is on your acyl derivative. So C double bond O, R is acyl. There's a leaving group here. You swap the leaving group for the nucleophile. The nucleophile in this case is the alcohol, the O atom of the alcohol. And so your final product is the acyl group, and then no more OH, that's your leaving group. Instead, you have O, that was bonded to this. And then what else do we have? We have OH that left, and then what left from the alcohol? H. And so what does H and OH form? Water. So I won't be expecting you to give that, but all of these reactions can be viewed as just swapping. So that's like A, B, and that's like C, D. This is essentially A, C, and B, D. You might have learned about like double displacement or double replacement reactions in, I don't know, maybe high school chemistry or something like that. It's basically the same thing, but an organic analog thereof. If that didn't make any sense, don't worry about it. But some people might have learned that in AP Chem. At least when I took AP Chem, they were big on double displacement or whatever it's called. All right, so this is an acyl derivative, so we can kind of apply that same logic here. So here is the acyl group. This in the product must have been the what as a starting material, not the catalyst, but so this is the same as that, right? So going from here to here, what left? Which must be Cl, so leaving group. In all of these acyl transfer reactions, what gets swapped out for the leaving group? What's reaction role? The electrophile or the nucleophile? Okay, well let's talk more. The leaving group is always bonded to what species in your reactions? The nucleophile or the electrophile? the electrophile. So think about SN1 and SN2, right? So an SN2 reaction with iodide. That is your what? Your leaving group. What is the carbon that's bonded to the leaving group? That's the electrophilic carbon. E minus carbon. It's the same thing in these reactions. Leaving group. The carbonyl is the what? Electrophile. So this whole part of the molecule is the electrophile. There's your leaving group. So what does that leave for what that was? Nucleophile. So what do I have to put in this box then? That plus a, so if it's NH, that doesn't give me a complete octet at nitrogen. That gives me 6 electrons at that nitrogen. I didn't write what else is over here, but it would have been HCl. So what else do I need here? H and H2. So this is an amine plus a acyl chloride gives you an amide. So this is going to be an important reaction tomorrow. You should know that amines will react with other acyl derivatives to give amides. I would highly recommend knowing that an amine with acyl derivatives makes an amide. You should also know how to draw a tetrahedral intermediate for that. So let's do that. What's the tetrahedral intermediate? Well, that's what happens when the amine first adds to the carbonyl. So amine, lone pair, goes to this carbon of the carbonyl, which breaks my pi bond. So your tetrahedral intermediate always has O minus. What else was at that carbon? A 1, 2, 3, 4 butyl group. 1, 2, 3, 4. There's also a chlorine on there. Chlorine, and then what did I just add from this bond? Nitrogen. And what was on that nitrogen? Well, we'll abbreviate that as phenyl H2. And so what needs to be on this nitrogen now? Yep, positive. So I would highly recommend, if I were the person designing an exam, I would be that person to recommend knowing the tetrahedral intermediate of an amine reacting with a carboxylic acid derivative. That could come up. It very much could. Okay. This is a carboxylic acid. What sort of carboxylic acid derivative is this? Acyl chloride, yep, acyl chloride. There's one reagent that will change this to that. If you went to OWLS, you might know the mechanism. You don't need to know the mechanism for the final exam, but does anyone remember the name of the reagent? Thionyl chloride, which does anyone remember the formula? SOCl2. Yep.
It's a sulfur.
Yep.
You have to know the formula or just have it draw the name?
Like this formula. Although, yeah, give me this. Give me this. Don't give me thionyl chloride.
Would you accept a drawing?
I would accept a drawing.
Okay.
Yes. Yes. Yeah. Okay. So I'm going to say this page is kind of important. So let's finish it up. This is an ester and hydroxide. If you ran the soap lab, you had fatty acid esters, olive oil plus hydroxide, and you got out a soap, which is a salt of carboxylate. So this goes to the carboxylate salt. So what the hell is a carboxylate? Well, carboxylic acid is this. Carboxylate, ATE, that suffix denotes an anion with a conjugate base. So O minus makes 8. Then sodium plus. What else would have formed? Well, you would have had CH3OH. So once again, what we've done is essentially swap that, and that, and that. So first, what you would get is H plus NaOCH3. That's plus, minus, positive. But when you have your carboxylic acid in the presence of strong base like methoxide, what happens to the carboxylic acid? It gets deprotonated to the carboxylate, and then you would have methanol. Okay, if you take this species and an acyl chloride are great what? Electrophiles or nucleophiles? This carbonyl is an excellent electrophile. You have an O minus here, that's a pretty good nucleophile. I say pretty good only because really this O minus is stabilized via resonance. Let's say that carbonyl wasn't there, that would be even more nucleophilic. But the carbonyl stabilizes it through resonance, so it gets sort of less nucleophilic. So, and all of these reactions, so that's the electrophile. What does that mean for the chlorine? What is that? Leaving group. So all you have to do is take the electrophile, bond it to your nucleophile. O, and then the electrophile has the carbonyl and the methyl group. And then what would you be left over with? NaCl. So I won't be asking for the byproducts, but you're free to give them if that helps you do so. That helps you remember the reactions. So I'd say this is a pretty important page. Oh, there's more. Okay. This is a tough one. Kind of. What do we have over here? What sort of functional group? Alcohol. What do we have over here? What sort of derivative? Carboxylic acid. What do we have right here? Yes, this is a really important thing. Really important. If you have something that looks like this is just an ester inside of a what? A ring. So this is just an example. Well, if you really want to know the name of these species, they're called lactones. That's just an ester that's part of a ring. But just because something's in a ring, that doesn't make it not an ester. So this is an ester. You can see O, C double bond O, bonded to R. It just so happens that that R eventually gets back to the carbonate. That's a really important thing. If you have an alcohol and a carboxylic acid going to an ester, what else do you need? What sort of reaction? This is one of those special named ones. Fischer esterification. Alcohol, acid, and then it's kind of difficult to see here, but H2SO4. This is a Fischer esterification. Okay, so what happens here? You have carboxylate going to a what? Not an alcohol because carboxylic acid, right? Not an ester because that's not carbon. So what do I add to that oxygen? Hydrogen. So what do I need here? So yeah, it's going to be HCl. So a hydride, remember that gives you H minus. We need though H plus, right? Because that is already a minus. So we need a source of H plus, which is an acid. So HCl, H2SO4.
Is that because, it's going to the oxygen instead of the carbon?
Yep, exactly. The carbon, when the hydride goes to the carbon, that is a delta plus. And so something that's a delta minus would go there. When it's at an oxygen, that's a delta minus, so it needs a delta plus. Obviously, a proton would be a delta. If it's got a formal plus, then it's for sure got a delta plus. So HCl, H2SO4. Here's another really important one. Ammonium chloride, that would work too. So ammonium chloride is NH4. Cl. Nitrogen is more electronegative than hydrogen. So actually all of those have delta pluses. The nitrogen actually has the delta minus, even though there's the formal positive there. Hydrogens that are actually acidic. So these are all acids that you could have put there for sorry, I guess I gave you sodium chloride, so you needed HCl. But generally speaking, if you want to protonate something, you're going to use an acid like this. Okay, so this is a ketone. This is a what? Ester. What have I added to the ketone? Hydrogen. So it was implicit. There's an explicit. So what sort of reagent did I use? A hydride. And if I didn't reduce the ester, which of the hydrides did I use? Sodium borohydride, NaBH4. And then I heard Susie say it. What do I need for the second step? Yeah, HCl, H2SO4, NH4Cl, just something to provide that hydrogen. Okay, in this case, I have a ketone and an ester. They both were what? Reduced, so they both received hydrides. How many did the ester receive? 2, yeah. Remember, all your carboxylic acid derivatives can receive two equivalents of hydrides or organometallics. But if I reduce both of them, which of the hydrides must I have used? The stronger lithium aluminum hydride. So lithium aluminum hydride can reduce both the ketone and the ester. Sodium borohydride can only do the ketone. What's this next step here? Let's just use a different one. We'll use NH4CO.
Something that's like an acid like this.
Right, something that's basically something H plus.
Does it have to be chlorine?
In this case, it didn't need chlorine because I didn't define a byproduct. Yeah. So it could have been H2SO4,
It's something strong.
just a strong acid, yeah. Okay, what sort of functional group is this? Yes. So this is a really important thing to know. Know acetals. Should know sort of the mechanism, like the arrows for that. Remember pad, ped. Know how to identify them, know the mechanism, or at least the arrows for the mechanism, and then know how to make it. So this part corresponds to this. So what must I have had over here? The rest of it, a ketone, yes. So an aldehyde or a ketone plus two equivalents of an alcohol or one equivalent of a diol. So what was on my ketone? There's my ketone carbon. Phenyl group, pH, and a methyl group, CH3.
What do you do? Would you be okay with us writing pH instead of drawing the ratings, or do you want us to do that?
Yeah, you can always do abbreviations. Yep. So, instead of an ethyl group, you could do ETO. I didn't really do that throughout the semester, but I'm fine with people putting that. Okay, mechanism. What did we form here? What sort of acyl derivative? An ester. Esters typically, or esters can come from, we know, alcohol plus carboxylic acid. That's a Fischer esterification. This one's a little bit different. Let's go ahead. This is a what? Not a ketone. So if it's not a ketone, it's a aldehyde. This is a what? Ester. Sodium borohydride will react with which of these two? Aldehyde. So arrow from the BH bond to the carbonyl carbon, which is the electrophile, which breaks the double bonded oxygen. That gives me BH3. So this boron lost its hydrogen. This hydrogen ends up at the carbonyl carbon, which lost its double bond. Now there's a formal what at oxygen. Then the rest of the molecule. Okay. Now, eventually we need to do what? Form a ring. So I have something that is, So what is this in an acyl derivative? Is that the nucleophile, electrophile, or leaving group? Leaving group. The carbonyl is the electrophile. O minus can act as a nucleophile. Have 1, 2, 3, 4, 5. What sort of ring do I have? 1, 2, 3, 4, 5. So what do you think happens in the next step? Yep. Ring formation or a cyclization. To do that, this oxygen, which is 1, needs to form a bond to carbon 5, the carbonyl. So that arrow shows lone pair, carbon 5. If I form a bond at carbon 5, I need to break what? The leaving group bond, yes, but does that happen right away? That's right. The leaving group bond is a sigma star CO. So if you want to break a CO bond, remember you need to put electrons into a CO sigma star. For a carbonyl, to break a carbonyl, you need to put electrons into a pi star CO. Pi stars are what? Lower or higher in energy than a sigma star? Lower. A lower LUMO is a better, it's like lowering a basketball hoop. It's easier to put electrons into it, electron receiver, right, which is another term for a electrophile. So the better electrophile here is the pi star, not the sigma star orbital. So eventually that leaving group will leave, but not right away. So we can draw out a new ring. Now, if I want to reform a carbonyl, how do I do that? I have to take one of these lone pairs and make it a what? Double bond. If I make a double bond, though, what has to happen? You have to break the CO bond. So now, those two arrows show that, then it would be plus, O minus over there. But we only really care about the lactone, or the ester. Okay. Ketone plus strong acid and what sort of molecule is this? There's two what's? Yep, it's a diol. And then what functional group do we form? Acetyl. All right, let's all pay close attention to adped. All right. P for protonation. I have a ketone. I have H2SO4. If I want to protonate my ketone, it needs to gain a what? A hydrogen. An acid, a Bronsted acid, is a what donor? Proton donor. So I need to form a bond between oxygen and hydrogen. So where should my arrow start? Oxygen at the what pair? Okay, and it needs to end at the hydrogen. And then if I'm going to take that hydrogen, what needs to happen over here? Yep, you need to break this OH bond. So lone pair to hydrogen, bond onto oxygen as a lone pair gives you these two species. What should be on this oxygen? Yep, minus. So let's just assume that this would be a very critical thing to know how to do. To take a ketone and a strong acid and protonate it. And what happens to the ketone carbonyl? What does it become a better of? So carbonyls are normally what? Electrophilic or nucleophilic? Electrophilic. Here it's acting as a nucleophile. Once it's protonated, it's become positively charged. So what has it lost essentially? Electron density. If something loses electron density, it wants to get back to being neutral. So it's become a better electrophile. So protonation, it would be a good thing to know that protonations make better electrophiles out of species. Okay. A for addition. Once that carbonyl has been protonated to become a better electrophile, this OH, which is a weak nucleophile, remember, if it was O minus, that'd be a very strong nucleophile. If it's OH, if it's neutral, it has electrons, it has the two lone pairs, but it doesn't have an excess of them, like having a formal minus charge. But it's nucleophilic enough now, such that it can do what to the carbonyl? Attack it. So where does my arrow need to start? Yep, at the lone pair of the oxygen. Where does it need to end? Yep, the carbon of the carbonyl. Then what needs to happen here? Yep, I need to break my carbonyl bond. That gives me OH OH plus all right. Deprotonation. Protonation, addition, deprotonation. Where do I have an extra proton here? On the diol oxygen, yep. So now I can take, honestly, I can take either the conjugate base of H2SO4, or I can take another equivalent of the diol. We'll take another equivalent of the diol, which is basically running a solvent of ethylene glycol. Act as a base. So if I want to deprotonate, where do my arrows need to start? At the base, which is here. They need to go to where? To the hydrogen. And then I need to break what? The OH bond. So protonation and deprotonation, it's the same arrows, it's just what perspective are you doing? You're deprotonating H2SO4, but you're protonating the ketone. Here you're deprotonating this intermediate, but you're protonating that. So it's the same arrows, it's a deprotonation or a protonation depending on what species we're interested in. So we're interested in this because eventually it's going to get to our acetal. So deprotonating. I'll go this way. Okay, pad protonation P. So if I just had an extra proton over here, let's not protonate that oxygen again, that'd be going backwards. I mean, we could technically protonate this oxygen, and in solution, that probably does happen, but all this is reversible. You protonate over there, that isn't gonna get us closer to our product, though. So which oxygen do we have left? Well, this one. So we're gonna protonate this one. Arrow starting from the oxygen, going to the hydrogen, and then going from the OH bond onto the oxygen there. Sorry, I'll try to make that better.
Could you use the H2S and do that? Other side.
So if you use the conjugate base here, then H2SO4 would be there. If you use this, use that.
So it's just use whichever one you use in the step before.
Yep.
Okay.
The whole point of this sequence of protonating that oxygen was to make this a better what? Leaving group, yes. In this step, E for elimination, I kick out my leaving group. I eliminate, so I form a double bond. Draw first, oh, gosh, like this. Okay. Need a formal positive charge there. From here, it's kind of difficult to see, but you can also think about, so you could just draw this, but I'm gonna draw a different conformation that hopefully makes it easier to see how you form your ring. So these structures are the same. All I did was rotate this bond there, just to show you that I have, 1, 2, 3, 4, 5. I have the same thing here, 1, 2, 3, 4, 5. And that's the 1, 2, 3, 4, 5 over there. Um, I guess pad had worked for the, this was technically for the Fisher esterification. But here we need to add into the carbonyl to form a ring. So I guess for this one, there's a second addition, it'd be pad P. Add, elimination, addition, pad P. And then what's the last step? D for deprotonation. So we'll just use water. You could use water, you could use another equivalent of the diol, you could use the conjugate base of sulfuric acid. Either way. That gets you to your product. Plus H2O plus HSO4 minus. So that is essentially H2SO4, so it's actually a catalyst of H2SO4 because you form acid again. But this would be a very important to know. At the very least, let's say someone gave you a template of all the steps and asked you to draw arrows. Let's say that happened on exam 3, and let's say it could happen on the final exam. Let's say that students should know how to do the arrow pushing. Let's say the template's given because this takes a lot of time to draw, but the arrows don't. So let's say Sarah asks a question.
I was gonna ask if you could go through, like.
Oh, repeat protonation.
Or just like if you could leave it up.
Okay, yes. P there. A, sorry, so A is that. Here. D is here. I'm putting it over the arrow, so that's step 1, 2, 3. 1, 2, 3, 4, which was P. Step E. 5. And for forming an acetal, yeah, there's a second addition step. For a Fischer esterification, you would have a hydrogen here and not an R group. And so you would just do a deprotonation to end it. But here, there's an addition, 6, okay, then 7. That work? Yep. All right.
Professor,
Yes.
for this, okay, the second A step.
Yep.
I know in the example on your notes, you can do the resonance form. Is that applicable here where the resonance form with the double bond to turn into a low carbon oxygen? You do the addition. That also work.
Yeah, you could show it from here if you want. So if you had this resonance form, then you just don't need the second arrow, right? Either one. It's something that if you did want to show, let's say you weren't hypothetically given a template that hypothetically didn't have this form. Let's say hypothetically you did draw these two forms. Then you would want to make sure that whatever arrows you're showing aren't showing the resonance, they're showing like the step going forward, right? So don't try to put like an arrow that shows resonance and arrows that show the steps that go forward. I can't, I can't figure out which is which. But if you were given a template that just had this one, make sure you do both arrows. Yep.
Before you go on, could you just clarify, like, in words what the purpose of the diol is in these reactions?
The diol, these oxygens are what form the ring here. So this ketone oxygen actually leaves as, well, in this step, it's water. So that's the ketone oxygen. So some of the cool experiments, at least I think in organic chemistry, are sometimes you can actually label, so oxygen is normally 16. You could synthesize a labeled ketone like this, oxygen 18. That's just one of the isotopes of oxygen. And then you could run the reaction, isolate the acetal, isolate the water, throw it into a mass spec. Normally water has a mass of 18. If you throw the water that you isolate from this reaction and you get out 20, then you know that the oxygen that had 2 more mass units to begin with must have ended up here. If instead of whatever the molecular mass of this is with oxygen 16, if instead the oxygen 18 is in here, then the mass would be +2, relative to what it would have been. So that's proof that organic chemists have had since mass spec has been around, that this ketone oxygen is the one that leaves as part of water. It's the diol oxygens that come in to form that ring. Kind of a clever trick or experiment. All right, so we didn't learn. I wish we did, but honestly, we learned a lot of stuff in this class, and any more would have been pushing it, I think. You all probably agree. We actually didn't learn about radicals. That's a whole nother topic that apparently Parsons and CHEM can fit in. In any event, these are imines. They're analogs of carbonyls. So in the same way that a carbonyl is a C double bond O, an imine is a C double bond N. A C double bond C is a what? Alkene. So they're all just analogs of each other. You're just changing one atom. C double bond C, C double bond N, C double bond O. So because they're analogs, they're kind of like brothers and sisters, or I guess that's the best analogy. They're going to have similar chemistry. If you can do addition reactions to C double bond C, an alkene addition reaction, if you can do addition reactions to the carbonyls, C double bond O, you can probably do addition reactions to imines. Because addition reactions follow the same mechanistic pattern, you're going to be using the same sorts of orbitals to do them. So in part A, what is typically the HOMO of a carbonyl? HOMOs are associated with what? Nucleophiles or electrophiles? Nucleophiles. So what is nucleophilic on a carbonyl? The lone pairs on oxygen. So that is your HOMO on a carbonyl, N sub O. What is typically your LUMO? What is that associated with? Nucleophile or electrophile? Electrophile. So what's electrophilic about a carbonyl? The pi star, the pi bond. So when you want to accept electrons at a carbonyl, you need to do it at the LUMO, which is pi star CO. In an alkene, doesn't have what anymore? Lone pairs. So the HOMO then goes to the pi bond. So if you remember your series of sigma, then pi, And SP, SP2, SP3, P, all of those, which we can just subsume into lone pair N. And then pi star, sigma star. So if you lost lone pairs, the next highest orbital is pi. So the HOMO of a alkene is pi CC. What is the LUMO? Yep, you still have a pi bond, so that's still the LUMO. For the imine, what do we think about the imine? So the HOMO should be the what? So so not a p orbital, but it is a lone pair. So what can we call n sub n? Lone pair on n. This is everyone's favorite question. Exam 1. If you have a double bond and a nitrogen, so that could be an imine, or it could be, within the ring. This is a pi bond, which needs electrons from what orbital? P orbital. So the p orbital electrons are in the pi bond, so what does that mean those are in? sp2. Okay, how about this nitrogen? What are those lone pairs? Same thing, sp2. I have a pi bond at the nitrogen. That only leaves sp2 for the lone pair. Okay, now we get to this one. This nitrogen, does it have any pi bonds? No. So where can those electrons be? In the p orbital. In fact, why do we want those in the p orbital? What? This is resonance, but even further down is aromaticity. You have a cycle, a ring. If this nitrogen is sp2 hybridized, it's planar. If it's sp2 hybridized, then you have a p orbital. With that p orbital lone pair, then you would have 2, 4, 6 electrons in the pi system. 6 equals 4n plus 2, when n equals 1. So that would be aromatic. So essentially, there's one thing in this class I'd like everyone to leave with. It's that nitrogen that's in a double bond, the lone pair is in an sp2 orbital. Nitrogen's not in the double bond, but it's next to the double bond, the lone pair is in a p orbital. I would feel very accomplished as a professor if everyone knew that. But I'm not confident. Sorry. That was me. I'm sorry. Anyways, I know people hate orbitals. Maybe next year, when I won't be here, but anyways. Okay, LUMO. So in a C double bond N, what is the LUMO? Pi star. So essentially, the only thing that's changing in this series is, oxygen and nitrogen, they have a lone pair, so their HOMOs are going to be the N, the lone pairs. And an alkene, you no longer have any lone pairs, so your default HOMO has to go down to the pi. Okay, and then how does the energy of the imine HOMO compare to the HOMO of a ketone carbonyl? Okay, so we're comparing N sub N versus N sub O. That was supposed to be comparing, but it looks like comparing. Comparing. The lone pair on nitrogen is so lower or higher than. So if you have a lone pair, oxygen is what? More or less electronegative than nitrogen? More. If it's more electronegative, oxygen holds the electrons closer to the what? If you have a minus charge closer to a positive charge in terms of energy, that is lower in energy. So the lone pair on N must be higher. Since O is more electronegative. Okay, comparing pi star Cn versus pi star CO. Okay, the pi star Cn. So goes way back to the beginning of the class, but essentially, as atoms become more electronegative, or as they gain more protons in their nucleus, all of the energy levels decrease, right? So the 2p orbitals of boron are up here. The 2p orbitals of fluorine are down here. Everything else is in between. So the atomic orbitals going from boron to fluorine decrease in energy because you gain more protons that pulls the electrons closer to the nucleus, which lowers them in energy. So the atomic orbitals of nitrogen, if they're here, where should oxygen be? Here or here? Lower. And so if you're going to form a bond, Cn versus CO, the bonds that carbon forms with nitrogen have to be what? Higher in energy. That's going to be systematic, basically, for all of the different orbitals. So the LUMO pi star Cn should be also higher. The atomic p orbital of nitrogen is higher in energy that of O. Okay. I'm going to draw a orbital diagram to explain, to show all that in 1 second, but which functional group is more electrophilic? So electrophiles are associated with which frontier molecular orbital, the HOMO or the LUMO? The LUMO. If you have a lower LUMO, it's easier to donate electrons into you, right? It's like lowering the basketball hoop. So if the LUMO of pi star Cn is higher in energy, that would make it basically like you're raising the basketball hoop, so it's more difficult to put electrons into it, which would make the CO LUMO a better or worse electrophile. Better. The So which one's the? Carbonyl of the ketone more electrophilic because its LUMO is lower in energy. So if you wanted to have a chart that summed up all of this, which I won't ask on the exam, I'll just tell you that flat out. Make a double bond, right? We're gonna have the sp2 and the p, sp2. Nitrogen is more electronegative, so the orbitals are gonna be lower in energy. P2. Then we also have, so we'll get the second one is going to represent the lone pair. So if I want to represent this, that's what's going to go here. So I'll have my sigma star, or excuse me, my sigma, my pi. I didn't give enough space. Dang it. sp2 sigma for my sp2s, pi's from my p's, sp2 from the lone pair, and then higher in energy would be pi star and sigma star. So in C double bond N lone pair, I have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And 1, 2, 1, 2, 3, 4. Oh, this is gonna be terrible over here. CO is gonna be even lower. I don't know how I'm gonna fit that. C needs to be the same in energy. O needs to be lower in energy for the sp2. I'll use 3 sp2s because I'll have 2 lone pairs. And one of them to make the sigma bond to the double bond. And my P needs to be lower in energy. And all of my orbitals for the molecular orbitals, that's pi. Your sp2 or N, technically when we make them molecular orbital, and pi star needs to be lower in energy. It's pretty bad, sorry. And sigma star needs to be lower in energy. Yeah, it's pretty terrible, but technically not needed for the answer. What I'm just showing is that oxygen, the atomic orbitals are lower in energy than the nitrogen atomic orbitals. And so all of the molecular orbitals of C double bond O with 2 lone pairs are also lower in energy than C double bond N with a lone pair. I am going to erase that though, just because I feel like it's a pretty bad drawing to have without me explaining it as I go. Okay. Oh, okay, I gave more on that. Okay, the pK values of protonated iminiums and a protonated ketone carbonyl given above, so 6 to 8, and then -7. Which of the two is a stronger Bronsted acid? Ketone. Why is that? You want a lower or higher pKa? Lower pKa. Is -7 lower than 6 to 8? Yeah. Protonated ketone. Okay, so which of the two has a more Bronsted basic lone pair? The aminium.
But aluminum doesn't have.
Yeah, sorry, right, it needs to be the imine. That, this was somewhat ambiguous. Which of the two? That should have been, imine slash ketone. Sorry about that. So if it's the weaker acid, weaker conjugate acid. Right, so its conjugate acid, the aminium, is a weaker acid. And so as the base, it has to be stronger. You could also think about weaker conjugate acid slash higher what? Higher pKa, yeah, I'm sorry, but in terms of the orbitals we just talked about. Not homo, right? So when something acts as a base, it's donating electrons, so a higher homo is essentially like having a stepping stool in a basketball game. You're closer to the net. So things with higher homos are more basic or more nucleophilic. Oh, okay, okay, so, explain why the more basic. Is more basic, that was not the best wording, but the N sub N is higher in energy as a homo because N is less electronegative than O. A higher energy homo is a better electron donor, which is a Lewis base. All Bronsted bases are Lewis bases. Therefore, the imine lone pair is not only a better Lewis base, but also a better Bronsted base. Or you could say, here you could say, or Bronsted and Lewis basicity are directly correlated. So not all Lewis bases are Bronsted bases. But all Bronsted bases are Lewis bases. So essentially you can correlate the two. Yeah, I guess that's how I would explain it. Better electron donor is a better base. Better base is what we were asked about. Okay. So in these acyl derivatives, where is the leaving group? Right, yep. So that's the leaving group. So we have O minus. We have S minus. For leaving group. So better leaving group is a what? Weaker or stronger base? Is a weak base. A weak base is the conjugate base of a what? Weaker or stronger acid? Stronger acid. So this is the leaving group. Here's the conjugate acid of the leaving group. This is a very important question, by the way, hypothetically speaking. The concepts in this question might show up on an exam given on a Thursday this week. The pKa of these is what? So that's going to be about 17. This is about 10.5. So which is the stronger acid? Yep, stronger acid. Therefore, weaker what? Therefore, better leaving group. Therefore, 10.5. Therefore, the carbonyl of this is a better leaving group. It's easier for that, well, to leave. It's easier to replace it, which would make that carbonyl more electrophilic. Okay, how about a resonance argument? So what is a more relevant resonance form? An O positive or S positive? And this is going to be a little bit, not necessarily trickier, but think about the ability of lone pairs to overlap with carbon 2p orbitals when you have an oxygen versus sulfur. Oxygen lone pairs in what sort of orbital? 2p. Sulfur lone pairs in what kind of orbital? 3p. overlap between two P with two P is gonna be stronger than overlap of three P. Three P. Two P. So that's better overlap. More relevant. This resonance form takes away positive charge from carbon. So it takes away what? Electrophilicity, which means by resonance, this should also be more electrophilic. It's the same argument that we had for acyl chlorides. So in acyl chlorides, we had this resonance form, right? That was also formed by overlap of a lone pair and a 3p orbital at chlorine with the overlap of a 2p orbital at carbon. That overlap is less strong than for oxygen in a 2p orbital. Since this resonance form took away electrophilicity, this is not as relevant of a resonance form. You actually have more electrophilicity in an acyl chloride than the rest. It's also because chlorine is the best leaving group. This is an important concept to be able to think about, that the higher or the lower pKa of the conjugate acid of your leaving group. So in all of the carboxylic acid derivatives, going from acyl chloride, HCl, to acetic acid when you have an anhydride, to HOH when you have an acid, to HOR when you have an ester, to HNH2 when you have an amide. Right? Leaving group. Man, I am ready for summer. I'm tired of drawing damn molecules. No, it's been fun. Right, leaving group. Leaving group. Leaving group. Leaving group. Leaving group. -7, 4-ish, 15.7, 17, 36 to the pKa's. The thioester was at 10.5, which would be here. SH 10.5. Which would mean, well, I did not give myself space. Everyone get what I'm saying here? The thioester would be less reactive than the anhydride, but more reactive than all these. So let's just say on the final exam that you might take, let's just say you had something else. Maybe it had, I don't know, maybe it had this, who knows? I don't know. Maybe it had that, think about it. Think about it, maybe biochemistry uses that. Nice little phosphates. Maybe that'll show up. Is that legal? It is legal. Biochemistry uses it. Anyways. I think this is the last page. Oh, How are we supposed to finish this? What? I mean, I know I can finish it. I mean, wow, okay. All right, we're gonna have to go into turbo mode, sorry. Damn, I made a good review package. Okay. We only know how to make acids in a couple ways. I'm gonna tell you that one of the ways is from an alcohol. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Yep. Here, this could have been K2Cr2O7, H2SO4, or KMnO4 with sodium hydroxide. You want to get to an alcohol from this is an ester. You need to add what? What are we adding to here? We lost carbonyls, but we gained hydrogens, which we need to be, well, we need HCl, that's right. Hydride, but which hydride for an ester? Yeah. So this is a tricky one. So you might want to think about doing the mechanism of how the hydride opens up the ring and reduces you down to a diol. That's a nice tricky one. Okay, you have CBr bond with magnesium. Where does magnesium go? Yep, between MgBr. So this is making a Grignard. This would be an important one to know. RBr with magnesium goes to RMgBr. Not too bad. That makes sense because we had an aldehyde that added, so the Grignard adds the aldehyde. And then, well, we don't quite know what we need here. In fact, I might have screwed this up. Come to think of it, we'll see. Okay, in terms of making acyl chloride, what reagent do we know will do that? SOCl2. What does it need to make the acyl chloride? Carboxylic acid. To get a carboxylic acid from an ester, first you can make a carboxylate with base, NaOH, but then in the second step, what do you need? HCl. And then what the heck was I asking? So I need, well, this is a Friedel-Crafts acylation, so Friedel-Crafts acylation. So I need some sort of yeah, it's silly. Yeah, this is impossible to answer because like I don't give you what you need here. And this could be like an infinite amount of possibilities. I think I had you guys, I think what the idea was to go to an alkene, maybe. Through dehydration with H2SO4. Maybe that's what I had you guys do. Ah, okay, no, I wanted you to oxidize up, but I mean, you couldn't have known that, I mean, so, sorry about that. I wanted you to oxidize up. So. We'll use PCC, why not? That was just badly designed, sorry, but then once you have these conditions, so this is an orthopara director, right? O/P director, this is a meta director. You only expect then to get that position or that position, but because it's symmetrical, it doesn't matter. We get OCH3. Yeah. So sorry about that. That's my bad. Oh yeah, I was excited to find this question. All right, circle the acetal and amides. So at the very least, you got to know your functional groups. Acetal, then amide. Two chiral centers. Okay. Provide the configuration. R or S. The good news is you can always guess on these, and you got a 50% chance. Technically, since there's two of them, you got a 25% chance of getting either, both of them right, but in any event, this one is a bit simpler. It's one, and then this is a carbon, that's a carbon, but this carbon's bound to a carbon, this carbon isn't. So that goes 2, 3, 1 to 2 to 3, counterclockwise, H on dash. So the implicit hydrogen is on the dash, so we don't. Oh, sorry. Thanks. Yep. Yep. Clockwise with H on dash. So that can stay as R. Okay, here. This is 1. That's 2. That's 3. Clockwise, H on wedge, so S. So remember, you have to be viewing the chiral centers with the H on a dash. Otherwise, you need to change whatever you get, you need to flip. So if it was clockwise, I was doing this with some classmates before class. I don't have anything to rotate, but with respect to you guys, this is rotating counterclockwise, but with respect to me, it's rotating clockwise. So essentially, if the hydrogen is on the wedge, you're viewing it from the wrong perspective of what you need. Okay, and then this is a really good question because there might just be templated mechanism questions like this. Thankfully, because there's the template, this is a little bit faster. I'm just going to keep going past 4. I mean, I'll just stay. I know this has been a long time, but you're welcome to stay as well. So what does this oxygen gain in this step here? And so where does it get it from? All right, start from O, go to H, and then what happens to this bond? Great. Actually, my proudest achievement as a professor would be if people do arrow pushing. I take back the 90. Okay, what happens in this step? What does this leave as? Well, not H2, but methanol, yep. And this oxygen loses a what? So, and it gains a what? Double bond, so. Zoom in on this. Double bond. That's bond to oxygen as a lone pair. Okay, and then 3 prime. Nothing actually happens in terms of arrows. All I've done is rotate this bond. I'm not going to have that arrow be there. Rotate to get 3 prime. So what did that make 3 and 3 prime? Conformers. Okay, so what happens in 3 prime to 4? I make a bond between nitrogen and carbon, so what do I need to do? Yep. All right, let me zoom in. Exactly. That's going to carbon, going to oxygen. Four to 5. This nitrogen loses a what? See you guys. So to hydrogen, onto nitrogen. So this oxygen gains a what? From oxygen to the hydrogen. Oh, I wish that I had given you a lone pair, but there should have been one here. What needs to happen from going from 6 to 7? Yep. Double bond. And what goes here? Break the CO bond. Then this O is there. So what do I need to do? Break the double bond. Then last step is a deprotonation. So okay. So you might really need to know how to do these templated mechanistic questions. They might show up twice on the exam on Friday, Thursday. They could show up twice. There could be 2 of them. Yep, see you. Does anyone have questions about arrows?
No, but I just think I wrote your exam.
Oh, it'll be in right tier 1 from 7 to 9.
Or even the place where we've been having lecture.
Yes, the place where we've had lecture. So I'll make that as an announcement to you. Yep, see you, Phoebe. All right, you all are gonna make this HIV drug. Good job. But to do it, you need a couple more steps. So you have this acid going to an acyl chloride. So what happens? What reagent? SOCl2. Then you have an acyl chloride going to a acyl Cl going to a what? Amide. So you need 2 reagents. you need the amine from here. So H2N. And then what down here? Some sort of weak base like pyridine. Here is, pardon me, PYRI, yep. It makes males go infertile. It smells bad. This would be a really good skill to have for Thursday, being able to predict multiplicities. Although maybe they'll even be multiple choice, so you don't even have to be able to like really predict, you just need to be able to match, potentially. So you want to predict the multiplicity of the protons. So here are 3 protons, that's the integration. What is the splitting though? How many protons are at the carbon next to it? 1, so the n+1 rule says those should be a doublet. How about here? There's the carbon, here's the carbon next to it. There are, so it should be a triplet. Here, if you go there or there, there's no carbon with the hydrogen, so there should be a what? Singlet. All right, good. Oh, another drug. Cool. So if you watch TV, basically I get excited when the drug commercials come out. I'm like, what's the structure of this? Oh, here we go. Hybridization of lone pairs. If you have a nitrogen that's in a double bond, the lone pair has to be in a, yes, yes. If you have a nitrogen that is next to the double bond, the lone pair is in a P, which makes this whole ring aromatic. In fact, this whole ring here is one aromatic system. Both of those are aromatic, so altogether it's aromatic. Oxygen is in a double bond, so the lone pair must be in a, yeah. Nitrogen next to the double bond. P. This nitrogen is what hybridized? So that must be sp, because the 2 pi bonds are coming from electrons in p orbitals. So it's just like, if nitrogen is in a double bond, the lone pair is in an sp2. Nitrogen is in a triple bond. Well, the p orbitals are still used to make the pi bonds, so now the lone pair is in an sp. Okay, Zeljans has some IR signals. By the way, you will have the charts of like the different ships and stuff. I could have done a better job communicating about this final, I'm not gonna lie. Maybe next year. So, oh no, I said that. I think I wrote it on the board. I wrote it on the board once. That's not bad, but it's not good. CH bonds, sp2 carbons, those show up typically above 3,000. So of these 3 values, what do we think? 3,100. Carbonyls, typically around 1,700. But if you have a factor like resonance, and in an amide, we know this resonance form is actually quite relevant. The lone pair that was used to overlap is in a 2p orbital, so that's good. And then a positive charge on nitrogen in terms of energy isn't that destabilizing. So this is actually a pretty important resonance form. It lowers the bond order at CO, so it goes from a double to a single bond. This is then a weaker carbonyl, it's a weaker CO bond, C double bond O. So it's going to be less than 1,700, so that would make it 1568. And then finally, 2853. So, you will have the charts, and you could have found those. Really, triple bonds are the only ones that show up around there, so. Oh, nice. One of the intermediates needs to make Xeljanz to be made from chloroacetylchloride below, chloroacetylchloride. Provide the missing reagent, the name of the mechanism of the reaction, and the air pushing mechanism for the reaction. Okay, you have an alkyl chloride. You have a polar aprotic solvent. Yep, NaCN. NaCN in a what sort of substitution mechanism? SN2, good. Arrows, white, simple, I think, relative to the ones that, now they are. Now that we've seen so many different sorts of reactions. From the nucleophile to the electrophile, break the bond to the leaving group. Cl, C triple bond N plus NaCl. This would be a good thing to know about SN2 reactions. Polar aprotic solvents, alkyl halide electrophiles, and some sort of nucleophile. So yeah, I typically make these exam reviews tougher than what the exam will be. And in this case, this is a pretty tricky one. And I'm not surprised that I put it because I do design it to be more challenging than the exam, but this is up there. Okay, so what do we have here in this molecule? What sort of functional group? Ester, yeah, that's an ester. The saponification reaction, I tell you that. I give you the product. I bet it's challenging even to draw this all, because it is for me even.
We're gonna have silly little things like that to draw in the exam, because it's only really hard.
No, there won't be, they're called bicycles, literally spelled bicycle. But they're, because you have two rings smacked together, there won't be any bicycles. I have tried, especially on the final, like streamline it such that the drawing is minimal. But back in my day, we didn't have professors that gave us templates. Anyways, so the ester is an electrophile to carbonyl. The hydroxide is a good what? Base, but in terms of a reaction that isn't an acid-base reaction, nucleophile. Dang, I had people asking me for the key, and honestly, after seeing this question, I can definitely understand why people wanted the key. Darn, I'm to drill. I spent a lot of my PhD working with bicycles. Okay, this is an acyl transfer mechanism. So what happens next? This is the tetrahedral intermediate. We need to reform a what? Not an aromatic. Double bond. And kick out a what? Leaving group. So now we don't have an annoying bicycle anymore. I'm going to do 1, 2, 3, 4, 5. Oh, whoops, that should be. 4, 5, there we go. Yeah, there's no way you could have got this stuff, with no offense. O minus. Like I said, I do make it more challenging than the test for a reason. Okay, so let me map things on for everyone. 5, oh, carbon. Darn it. Even I can't do it without a key. Five, 4 here, 3, 2, 1. And then in the last step, another equivalent of OH minus. Deprotonates this. Going to draw. P.J. Corey's a big deal in organic chemistry. He was like probably one of the top 5 of the last century. And then, oh, this is still minus. HOH. Move that there. You get, so plus, you get to product. So essentially, these last 2 steps are just taking the proton that was here at the more acidic site, taking it to the more basic site. Yeah, that was tough. Okay, and then why the stereochemistry? So you can kind of see that here in the 5-member ring, this group at 5 is opposite to the group at 4 and 1. So 1 and 4 are on a wedge, and 5 was on a dash. Okay, then provide the mechanism in the second step. Okay, so we have an alkene plus, I give you I2. I give you a hint, it can form an iodonium ion. So what do we think happens in the first step of the mechanism? Form an iodonium. So the cool reaction. Difficult, yes, but very cool.
Question with like this much very complicated drawing thing or no?
This much what?
Like complicated drawing.
No. Oh, that's H. I, to form an iodonium, a 3-membered ring, you need a bond, double bond to iodine back to the double bond, and then lose an iodine there to get iodine plus. And then. All right. Iodonium. Here we need to form a ring with that oxygen. What do you think happens? Yeah, that's exactly right. What does this kind of remind you of? Halo what formation? Yeah, halohydrin or halo ether formation. This is an intramolecular example where the nucleophile is part of the molecule already. If you had water or an alcohol around, that would have attacked this. But since we already have a nucleophile in the same molecule, it's much easier for that to come in. And that goes directly to the product. This is called, just don't need to know this, but an iodolactonization, because you had an alkene in which you added an iodine and then a lactone, which is a cyclic ester. So iodolactonization reaction. Well, then I just got bored and said, give a bunch of examples. Okay. Example with an SN1, sure, let's do a tertiary alkyl iodide plus CH3OH with heat going to a tertiary alcohol plus HI. So tertiary substrate, weak nucleophile, heat. Example that occurs with E1, well, I guess we could use the same substrate. I plus CH3OH. And then you'd go to that alkene plus CH3OH2 plus I minus. So an aromatic compound will do is an ortho pair director and a meta director on the ring and a meta relationship to each other. Okay, so I need a group there and a group there to be meta. I'll have my meta director be NO2 and I'll have my ortho pair director be methoxy. So that's OP. That's meta. Three-membered ring, aromatic. That's aromatic. Five-member. That's aromatic. 2, 4, 6. Here that's 2. So remember 4n plus 2. This is n equals 0. N equals 1. That's 7-member. 7-member rings are the worst. Also n equals 1. All of them have sp2 hybridized carbons all around and have the correct number of lone pairs or pi bonds. Draw a molecule whose LUMO is sigma star CBr. How about that one? Alkyl bromide. Draw meso compounds. We'll do the one that we had from lab. That would be good to know that that's meso, which is achiral. And then what does it have? A what center or what point? Inversion, yep. That'd be something good to know. I'd have that in your back pocket. C3H5Cl. So questions like these, I think it's actually good to calculate degrees of unsaturation. So 2 times 3 plus 2 minus the sum of H plus X, which is going to be 5 plus 1, plus any nitrogens, 0, divided by 2. So that's going to be 6 plus 2 is 8, minus 6 divided by 2. 8 minus 6 is 2 divided by 2 equals 1. So I just need one double bond or one ring. So I can draw, I know that has C3. I know that's my chlorine. So the hydrogens take care of themselves as long as they have the correct degrees of saturation. How about that? How about that? How about that? Technically, then you could also do the isomer. Oh, whoops. I think that's all of it possible. Alkene hydration reaction. Okay. This isn't a very good one, but you need H2SO4 AQ or H2SO4 H2O. Heck, let's make it a good one. Protonate the alkene, which puts the positive charge, the formal positive charge next to the phenyl group because of resonance stabilization. Then you get your OH there. This was a very long-winded way of saying what? What should this molecule have? Yep, chlorine. Any molecule with chlorine will do. I'll put a few. Anything. Well, draw 1 R, 3 R, then draw its 2 chair contours. Okay. So I need a chlorine and a methyl group. Now I need to figure out wedges and dashes. So let's just try putting the chlorine on a wedge, see what happens. So that goes 1, and this carbon will be closer to here. So that's 2 and 3. That's R. That's good. And then for this one, let's try putting it on a wedge and see what happens. So this should be 1, that should be 2, that should be 3. That would actually give me S. You can see that? Yeah. So I need to put it on a dash instead. That would give me counter clockwise. But H on wedge. So now it's R. 2 chair confirmers. Yo. H. H. H3C. Then fluorine goes equatorial up. And then the methyl goes axial down. That was bad. Which of these should be more stable? Yeah, the first one. The methyl group is larger than the chlorine group. So this would be a good thing to review. How to draw chair conformers. Do R and S. Draw the enantiomer of the molecule in part J, give its IUPAC name. So I need to draw what needs to happen to the chlorine. Yeah. Yeah, that's bad dash. How do I give myself space? And then what needs to happen here? Yeah. Perfections. But being able to quickly identify stereochemical relationships by switching wedges and dashes, that'd be a good skill to have. IUPAC name, so if that was 1R, 3R, this has to be 1S, 3S, 1 chloro, 3 ethyl, cyclohexane. Oh, good job. Draw diastereomer. Okay, so there's 2 of them in part, or yeah, in part J. So, yep, just switching 1.
So just like, you have to, like, would you have to drop over for that?
No, so one or the other. So this would be 1S3R. This would be 1R3S. And then the molecule part K. Do dot 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 equals 1 methyl like hexane. So 1S3S is also a what to 1S3R. And 1S3S is also a what to 1R3S. Diastereomer. Yep. All right, that is all of Chem 205. Not really, but Questions on the review packet, questions on stuff about the final?
Can you write us down a list of all the things that we provided?
Yes. The people who tune in later, I'll make an announcement tonight, but, P table for periodic table. 1H. And 13C. Chart. IR. Chart. And then P38 table. And then 2 scrap sheets. Now, obviously, you can have your 15 note sheets.
Where are the note sheets linked on the front page?
Yes, they should be inside of the. Pardon me?
Yeah, but like, where are they?
They should be in the exam folder, I think, but not in any specific exam. I think it's just. Yeah, note package sheet, right there. And then I think, does that seem? And then I don't remember what that paragraph says up there, but for the final exam, you can use as many boxes as you want for a concept. Susie?
Can you tell us like roughly how long the exam will be relative to the other?
Well, there's 4 questions. I think it'll be 1.5 to 1.75 times as long, so not fully twice as long, sorry. Not fully twice as long. But like maybe 1.5 to 1 3/4 as long. At least that's what I aimed for. I was making assumptions about how long it takes to do things, but I think you'll find that even if there's a lot of stuff, I don't actually ask you to draw a lot of stuff. If that makes sense. Like, I don't have you draw a lot of full structures. Jack?
Like 15 note sheets.
Yes.
Does that mean like 15 individual papers with the 4 boxes?
Yeah, yeah.
And then. Is it still required that the boxes left in like colors that you specifically bolded?
Yes, specifically bolded review sheet concept. But honestly, I haven't been checking people's notes sheets and like. You can probably, I mean, you can fit, like all the concepts, like you can definitely find something to fit in what you need. Yeah. Yep. So 7 PM in the normal room we've been having lecture. Unless you have, ODA saying otherwise. Yep, no problem, Susie. I'll get this uploaded to, Blackboard. Before, 7 or 8 PM. Since this is a long video, it's gonna take a while to convert to the